Hello, my Math75 algebra doing friends. Here we are looking at 8.2, simplified form of radicals. And here's some square roots I think that are pretty nice to know. Those are the ones that I also recommended that you knew when we were doing factoring the difference of squares. And here are some cubes that are pretty nice to know as well, perfect cubes. And those are the same ones that, when we were factoring the sum and difference of cubes, that we said were good to know. And then there's a property that we're going to be using, and that is if you have the nth root of a, so it could be a square root, or it could be a cube root, or it could be a fourth root, and the nth root of b, now it would be the same. They would either both be square roots, or both cube roots, or fourth roots, or both fifth roots, whatever root they are. Then the nth root of a times b is equal to the nth root of a times the nth root of b. And the simplified form of radicals, they always tell us when they ask us to simplify stuff, what do they consider it to be? What do they consider to be simplified? And here they're saying that none of the factors of the radicand under number 1, the quantity under the radical sign, can be written as powers greater than or equal to the index. That is, no perfect squares can be factors of the quantity under the square root sign, and no perfect cube. And so just so that you know what they're saying here on number 1 is that you can't have the square root of 20 and say that's simplified, because one of the factors of 20, factors are things that divide evenly into it. Now, of course, 1 is there, but other than 1, we're not interested in 1 because everything has 1 in common. But 2 is there, and 4 is there, and 5 is there, and 10 is there, and 20 is there. Those are all the things that divide evenly into 20. And what's the problem is that one of those is a perfect square other than 1, and that's 4. It's in my list of perfect squares. And so that's the reason it's not simplified. And so that's what they're saying in number 1. In number 2, they say there's no fractions under a radical sign. So it would not be simplified to have the square root of 2/3, because that would be a fraction under a radical sign. And then they say that it is not simplified to have radicals in the denominator. So for example, 3 over the square root of 5 would not be simplified because there's a radical in the denominator. 3 over the cube root of 5 wouldn't be simplified either because that's a radical in the denominator. Okay, so in 8.2, they actually focus on how to fix up, how to make it simplified, number 1. And there are actually 3 methods, and I'm going to show you both methods. And so you make a good pile and a bad pile, and you take the root of the good pile. So you have to know your perfect squares to do this. And so when I say make a good pile, I mean make a good pile that is a perfect square. So in the case of 20, 4 is a perfect square, and so I would write it as 4 times 5, and 4 would be my good, that's my perfect square, and 5 is just what's left over. And then I can take the square root of 4. And so that's one way of doing it. And then another way to do it is to use prime factoring and circle in groups of the index. And then you can use a mix of both methods, which is usually you can't mix 2 methods together and have it work out, but it works pretty good here. So this is the example we're going to start off with, is the square root of 75y to the 5th. And so I'm going to try the good pile, bad pile. Now in good pile, bad pile, I have to know my perfect squares. So I have to know that 75, well, 75, the factors of it are 1 and 3 and 5 and 15 and does 15 go into 75? I think it does, doesn't it? You're like, you don't need to know if it does, for sure it does. 25, right? And there are more, right? Maybe. But 25, that's the one I'm looking for because it's a perfect square. So when I go to write this, I want to write this as, this is going to be my good pile, 25. And then over here, this is good. And then over here, I'm going to put what's left over. So 25 times 3 is 75. So I'm going to put a 3 there. So I still have 75 underneath the square root symbol, but I have separated it in, I don't know if you have to call it good pile, bad pile, or if you could call it perfect square, non-perfect square, right? And then remember that a variable raised to an even power is a perfect square. So y raised to the 5th is not a perfect square. And so I want to break that apart, just like I did the 75. And so I'm going to break this apart in y to the 4th times y to the 1, right? Because 4 plus 1 is 5. And this is even. So now y to the 4th is a perfect square. And then the property that they gave us said that when you break it apart, then you can take the square root of 25 y to the 4th times, and then the square root of 3y. You can take the square root of the pieces. And the square root of 25 is 5, and the square root of y to the 4th is y to the 2nd, right? And then I get the times the square root of 3y. And then there I have simplified it. And that is good pile, bad pile method of simplifying it. Now I want to show you prime factorization method of doing it. So when you use prime factoring, you say to yourself, let's see, 75, that's 3 times 25. And that's 5 times 5. So this is 3 times 5 times 5. And then those y's, and I'm right now grateful that there's only 5 of them and not 27 of them. And if there were 27 of them, then I think that I would want to think of a way other than writing them out. And now I'm going to circle them in what the index is. The index here is 2. It's a square root. And so I'm going to circle them in groups of 2, and I'm going to be unsquaring. That's what the square root does, right, is unsquare. So when you square something, you write it twice. And so when you unsquare, you're going to go from something that's twice to once. And when you're thinking about it, 5 times 5 is 25, and the square root of 25 is 5, right? And so I'm going to take the square root of this, and I say for every 2 that are the same, 1 comes out. And so I took the square root of the 25. And then I'm going to do that with the y's, circling them in groups of 2. So a y comes out, another y comes out, and then that poor y is stuck underneath there. It doesn't have a friend to come out. And so what we have left over underneath our square root is 3y. And then I would want to fix up 5y, that's 5y squared. So 5y squared times the square root of 3y. And you notice that we get the same answer. So we used a different method, but we got the same answer. And both methods are good, and you can even mix the methods a little. Anyway, so that's kind of your choice. Now, one thing that happens is when you take a cube root of a negative, I'm looking at this example now. When I take the cube root of a negative, that's a negative, and I don't write it. I don't write that 3 times or anything. I use my thought. What raised to the 3rd equals a negative? Well, a negative raised to the 3rd equals a negative. And so if I was going to use let's say I wanted to use the prime factoring method on this one, then I would be saying, okay, let me see here. The cube root, negative, and then 32 is 2 times 2 times 2 times 2 times 2. I know that 32 is 2 to the 5th. You back from your run? Good. And then a to the 6th is a, 6 of them. I've got 5 of them. And then I'm going to be circling these in groups of 3, right? So I'm going to first take the cube root of the negative, and that's a negative. And so I'm done with that. And then I'm going to take the cube root of those 3 2's. Now, those 3 2's, 2 times 2 times 2 is 8. So I'm really taking the cube root of 8 there, which is 2. But for every 3, I'm uncubing. So for every 3 I have, every 3 2's I have, 1's going to come out. So a 2 is going to come out. There's only 2 of them, not enough. And so the A's are going to get circled. So there's 3 of them. So an A comes out and another A comes out. So we're going to get all of the A's. And then stuck underneath our cube root symbol is going to be, we got rid of the negative, we pulled it out, we got a 2 out, we left those 2 2's, 2 times 2 is 4, and I just want to clean that up. A times A is A squared, so this is minus 2A squared, and the cube root of 4 times the cube root of 4. And there we would have our answer. Again, our variables are positive numbers. And so this wouldn't be important on a cube root, but it was important to us on a square root. And we're going to look at an example today which where our is not positive, not non-negative, and we're going to have to do some different work on it. This one's a 5th root. And so 486 is a pretty big number. I don't know what the 5th root of 486 is. And so that's a good time. I would do this method until I was like, I don't have to write those out. That's what I would do. So 486, so I'm over here on my scratch paper, and I'm thinking, well, 2 goes in there. So here I got 486, and I divided it by 2. So I got 2 times 243. And you get where, when you've done these, that you start recognizing numbers. And so 243 is actually something I recognize. 2 doesn't go in it again, but 3 goes in there. So divide by 3, 81 times. And then 3 times 27 is 81. And then 3 times 9 and 3 times 3. So 286 is 2 times 3 times 3 times 3 times 3 times 3. How many 3's are there? 1, 2, 3, 4, 5, and then times 2. I just want to make sure. So 3 to the 5th, because there were 5 3's, times 2, and I want to make sure, yeah, 486. Okay, so I didn't make a mistake when I prime factored it. So I'm going to have here, under the 5th root, 2 times, and there were 5 3's. And there are 6 A's. And you can see where, when you circle them in groups of 5, that you can kind of see where, oh, I know what I could have done. I know when I was going to write 6 of them that I was going to have one group of 5 and one left over, right? And so that's when you're starting to get yourself going towards this method, is when you start thinking that way. 8 of them, boy, that's going to take me some moment to write 8 of them. So there's 3, 4, 5, 6, 7, 8 of them. Oh, 9 C's. Are you kidding me? I'm not going to be able to write that all in a line. C, 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 C. Okay, so I'm going to be circling these now in groups of 5. And so there's not enough 2's to come out, but 3 comes out, right? And so whatever that number is, if it was actually 243 is the number it was. The 5th root of 243 you might have not recognized as 3, but you'll get where you're like, oh, I think that one's built of 3's. So this is a 3. And then on the A's, we're going to have 1 A is going to come out and 1 A will be stuck underneath. We have 8 B's, and so 1 B will come out when I circle them in group of 5, and 3 B's will be stuck underneath. And the same with the C's. 1 C will come out, and stuck underneath will be 4 C's. That's not enough C's to get another group of C's out, because it have to be in groups of 5. And then this will be times the 5th root, and we have a 2 left underneath, an A, 3 B's, B to the 3rd, and 4 C's, C to the 4th. And then that's our answer in simplified form. Anyway, so that's what they were having us practice there. And then here, they're asking us to practice using this formula that has a square root in it. And I have, in block 1, some practice using some formulas with a square root in it. And so that's what we're going to practice here, right? And so you might have already practiced that. And that's great if you did. So when we plug in to our formula, so here's our formula. It says b squared, so I'm going to put a parenthesis for b squared minus 4 times a times c. So our b was 4, so I'm going to put a 4 in there, and our a was 1, and our c was negative 3. And then I just want to simplify that, right? So this is 4 squared is 16. And then a negative times a negative in here is going to be a plus, and so that's 12. 4 times 1 times 3 is 12. So this is the square root of, is that 28? Of 28. And then now I can either use prime factoring or I can use good pile, bad pile to figure out the square root of 28. So some of you might be saying, oh, well, I know 28 is 4 times 7. And the square root of 4 is 2. So this is 2 square roots of 7. And some people might be saying, well, how I would have done it would say that 28 is 2 times 14, which is 2 times 7, right? Prime factor it, and then circle them in a group of 2. So a 2 comes out, and stuck underneath is a square root of 7. So however you do it, you get the same answer. So it's your choice on that. So hopefully my family will get the telemarketer. Okay, so we're going to try this next problem with the same. If you're thinking, well, where did this formula come from? What is the deal with this? This was 2 ways of doing it, by the way. Was an or, right? You don't have to do it both ways. It was an or, whichever way that you wanted, you get the same answer, right? And so this formula, this part of this formula here is from the quadratic formula, which we're going to be learning in chapter 9. And it's a famous formula. And so you guys will be happy. So this is the square root of b squared minus 4 times a times c. And when we go plugging in, we're going to plug in b is negative 2, and a is 6, and c is 5. And so we're going to get here negative 2 squared right there is 4 minus, 30 times 4 is 120, so I think that's 120 minus 120. 4 times 6 times 5, yeah, it is 120. So I'm getting the square root of 4 times minus 120 is the square root of negative 116 is what I'm having. And you guys remember that if you take the square root of a negative, do you guys remember the square root of negative 116? What's my calculator going to say? Ooh, I got pushing a different button there than I meant to push because I wasn't all the way down equals, right? My calculator says math error because this is not real. So it's not a real number there. Okay, so we did a lovely job on that. If you're wondering, hey, well, my calculator, could I have put this one in just like I saw it? The square root of 4 squared minus 4 times 1 times negative 3. And would my calculator have done it? And the answer is, yeah, it would have. Do you guys notice that? It went all the way to the answer. Anyway, so that's pretty nice. Okay. So more practicing problems that they have some that have some fractions in there. The square root of 75, it seems like we've done the square root of 75 today, right? The square root of 75, remember we said was the square root of 25 times 3, which is 5 times the square root of 3, right? So the square root of 75 over 5 is the square root of 75 is 5 square roots of 3 over 5. And then 5 divided by 5 is 1. So this is 1 square root of 3, which is the square root of 3. 1 times the square root of 3 is the square root of 3. So we did a lovely job on that. Using the square root of 75 again here, we're having 10 plus, and the square root of 75 was 5 square roots of 3 over 5. And two ways of doing it, if you like. One way that your book does a lot is they say that because 5 is a monomial, you divide the pieces. 10 over 5 plus 5 square roots of 3 over 5. And of course you could do that with your head. And 10 over 5 is 2. And the square root of 5 over square root of 5. 5 divided by 5 is 1. So this is plus the square root of 3. So 2 plus the square root of 3. If you were wondering, well, how will my calculator do on that? And so here I am going to put my 10 here plus the square root of 75 and divided by 5. And your calculator will do it. It is real important that you're able to show the work by hand and do the work by hand. And so it's kind of like, you know, people have different opinions, but when a person is going into STEM, it's very important that they can kind of do these kind of things by hand and know what the calculator would do. And then after they get where they're good at it, they can use the calculator to do it. So I always ask you to do it by hand. Many people would take your calculator away from you so that you couldn't even verify that you had the right answer using your calculator. But I ask you to show this work. And so I want to see this work so that I know that you're doing the work by hand. And so it's very, very important. I don't take your calculator away from you. Now the square root of 64 on this problem here, now 64, that's 8 times 8, right? And so I'm thinking here, the square root of 64, that's 8. And I'm thinking, oh my gosh, are you serious? Is that what that is right there? And it is, right? There's no more square root. After you take the square root of 64, there's nothing left over like there was when you take the square root of 75, because 64 was a perfect square. And so this is -6, subtract, and then the square root of 64 is 8 divided by 4. So that is -14, right? -6 minus 8 is -14. So this is -14 over 4, which is -7 over 2. And we did a lovely job on that. And so pretty good. And then they tell us, hey, you know how when you had the nth root of A and the nth root of B, this could have been a square root for both of them or a cube root for both of them, that when you had a product that you could tear it apart and do the pieces. Well, now they're saying if you have a quotient, if you have a division, you could tear it apart and do the pieces. And so how that's helpful to us is that you can think of this as the square root of 20 over the square root of 9. And then the square root of 20 isn't simplified because, and I'm thinking this in my head, because 20 is the square root of 4 times 5, right? That's our perfect square in there. And the square root of 4 is 2. So that's 2 square roots of 5. And so this becomes 2 square roots of 5. And what's the square root of 9, friends? Yeah, it's 3. And then that's it. So we've simplified it. Remember, when we simplify things, under condition number 1, I know it's been a while since we did the conditions, right? Under condition number 1, the square root of 20 wasn't simplified because it was 4 times 5, where 4 was a perfect square. And under condition 2, no fractions under the radical sign. And so 20 over 9, the square root of 20 over 9 was not simplified. So I rewrote it so that it was the square root of 20 over the square root of 9. Then it wasn't simplified because no radicals in the denominator, and here I got the square root of 9 in the denominator. But good news, the square root of 9 was a perfect square. And so you might be thinking, well, what if you hadn't got rid of the radical in the denominator? What if it hadn't been a perfect square, the square root of 9? Then I would have suddenly woken up and been in the next section. And so we'll be trying that. If I could have reduced 20 divided by 9, that would have been an okay move to do as well. 20 and 9 don't reduce with one another. And I'm not sure about 1458 and 3, whether or not they reduce with one another. I'm thinking they do, right? I'm thinking that because there's that secret of how to know if a big number is divisible by 3. There's the use your calculator secret, divided by 3, right? And there's the secret of adding the digits. 1 plus 4 is 5, plus 5 is 10, plus 8 is 18. And since 18 is divided by 3, that number is also divided by 3. But I want actually to know the answer, so actually doing it on my calculator is a good way. So whenever you have the fifth root, or even a square root, it doesn't matter. And if you can divide it, that's okay to do first. So I'm going to divide this. So it's still a fifth root. I haven't done anything about that. But I'm physically dividing 1458 divided by 3. So that's 486. A to the 9, B to the 10. And I'm supposed to take the fifth root of that. And so using my property, that's the fifth root of 486, a to the 9, divided by the fifth root of b to the 10. And the fifth root of b to the 10 is a perfect fifth root. If you think about writing all those out and circling them in groups of 5, do you guys agree that when you wrote them out there would be 10 of them, and you would circle them in how many groups of 5? Would you circle them in? Yeah, 2 groups of 5. So for every group of 5, a B is coming out, right? So you could write it if you needed to, right? You could write it like this. I'm not saying you have to. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And you could say, I'm going to take the fifth root here of those 5, and that gives me outside a B. And outside of the fifth root, because I took the fifth root, now I'm going to take the fifth root of those 5 b's, and that gives me another b, so times b. So on my denominator, I have b squared. Now my numerator isn't so friendly, and 486 isn't somebody I recognize. I was thinking 243, because remember that one, we had that one before. But so I'm up here, 486, and I'm thinking, well, I'll prime factor it. 486 divided by 2 is, oh, didn't 243? Didn't we learn something about 243 a little bit ago? Because here I've come across 243 again. I think that we learned that it was 3 to the 5th. Do you guys agree? So that if I was to break this down, I'm just going to write what I remember it was. It was 3 to the 5th. So let's make sure that it is 3 raised to the 5th, because that was a memory, right? So 3 raised to the 5th, is that 243? Yeah, it is. It's 243. So this would be the fifth root. I feel like I need to get, it's like I'm trying to write small and I got a crayon that I'm writing small with, and that's not working out. 2, and then I can either write that as 3 to the 5th, or I could write 5 of them. And if you're like, I wish you would have written it to the 5th, then that's the good news, is that you can write it to the 5th yourself. And then I've got 9 of those A's written out. I'm going to have to write this down right below. So BB, right? I ran out of room. And when you guys are unneat like that and you scribble it out, I get all over you. So here I'm getting my white out, and I'm fixing it and making it neater. Your work matters to people. And so And so I fixed that up and made it look a lot better there. And now I'm going to start circling in groups of 5. And I don't know if this pen is going to work. So 5 3s, so a 3 on the outside. And if you had 9 A's and you circled them in a group of 5, you're going to have an A on the outside and 4 stuck on the inside. So that's going to be the 5th root, and we had a 2 left over, and 1, 2, 3, 4 A's, A to the 4th. And so when this is all cleaned up, 3A, the 5th root of 2A to the 4th, over b squared. And then that's it, right? So that's all that we can do. And so it's our answer. It's simplified because there is no radical in the denominator. There is no fraction underneath the radical. And this radical, which is a 5th root, there is no perfect 5th root underneath it. We got it all out. We pulled it all out. So that's it. And so we're all done. And so 8.2 is a longer section, and I'm going to try to do these 2 problems and then put the rest in a different video. So remember that our property said that that if you have a root divided by a root, that you can put them underneath one root. And the reason I would want to do that here is because 707 reduce with one another. So I could put this underneath one root, and that'd be 700x divided by 7x. And 700 divided by 7 is 100, so that would be the square root of 100. And x divided by x is 1. And so this becomes the square root of 100, and the square root of 100 is 10. And then I'm done. Your calculator won't do that, right? You can't put that in your calculator just like you see it and have it do that. And so this one is a similar problem. It's a 5th root. Calculator actually doesn't do that good on 5th roots, even if you don't have variables. And I'm noticing that 64 divided by 2 goes. So I'm going to write this as 1 root. And so here 64 over 2. And a to the 11th over a. I'm kind of just spacing them out so that you can see I'm thinking about them. B to the 28 over b to the 3rd. So when I do the division, 64 divided by 2 is 32. So this is the 5th root of 32. And then when I do the division here, now that's a to the 1. So this is, remember the quotient rule, you subtract the exponents. 11 take away 1 is 10, a to the 10th. And remember, subtract the exponent, so 28 take away 3, that's 25. And I haven't taken the 5th root yet. All I've done is simplify the pieces here. And now I'm going to take the 5th root. The 5th root of 32 is 2. Do you guys remember we've done that? And the 5th root of a to the 10, now imagine writing them all out and circling them in groups of 5. You're going to get 2 groups of 5. Do you guys agree? An A will come out, an A will come out. And the B's, if I wrote them all out, I'm circling them in groups. And a B's coming out, right? How many groups? 5. If you're saying, couldn't you have taken the 10 and divided it by 5 to get 2? You're right. That's a cool way of doing it, huh? 25 divided by 5 is 5. That's exactly right. Okay, my friends, the rest of chapter 8.2 will be in the next video.